Hello, friends.
Hello, Mr. Stone.
It's good to have all five of you here. Apparently, everyone else got what they needed yesterday. But we can go over stuff as is required. We have 2 weeks worth of stuff, really, because last week's Zoom, we pretty much only talked about the angular kinematics stuff. The torque, which was new then, I kind of brushed over. So any of the stuff from this week's worksheet or last week's worksheet is fair game. And then if you want, we can also go over the gizmo for this week. But first things first, does anyone have a particular question from last week's gizmo, not gizmo, last week's practice sheet that they want me to go over? If so, if you could throw that out now. Nobody? All right, fair enough. Then in that case, how about I do one that I got asked yesterday when I posed that question, so that anyone who is watching this at least gets something from it. All right, if you can see this, I'm gonna go over this top one. A rigid uniform bar of mass 90 kilos and length 5.1 meters is supported by two vertical massless strings. So string B here is tied to the floor and keeps this end held down. String A is tied to the ceiling and is holding that part up. First of all, there was a key word in there. A lot of times with your physics problems, there are key words that are like flashing neon lights. They're hints as to how you have to go about this. In the first sentence, what is the key word that tells you something you really need to know? It's uniform. If a bar is uniform, then where is its center of mass?
The center.
Absolutely correct. So when it tells you that it's a uniform bar of mass 90 kilograms and length 5.1 meters, that means that at the midpoint, the weight of the bar is acting. So the midpoint would be right here. And I'm lazy today, so I'm going to use 10 for gravity. Lord forgive me, but I'm back on my 10 meters per second squared. So if this has 90 kilograms of mass and we use 10 for 1g, then this would be 900 newtons. And also this is at 5.1. Then string A is 1.2 meters from the left end of the bar. And string B is all the way at the left. And 4.9 from the left end, we have mass 2. Mass 2 is 2.5 metric tons. That is 25,000 newtons of force. Okay. With that, we need to make this into a torque problem because right now we have two unknown forces. If there was only one unknown force, then we could just use the sum of forces because we know this thing has to be balanced. It's not falling. So let's say that we only were missing string A. Well, string B, 900 newtons and 25,000 newtons are all holding it down. So if you treated this like a free body diagram, the only upward force must cancel out all three of those. So if you had these three, you could find this one, but we're missing one. There's a trick to that, though. And the trick is that since torque is force times lever arm, if you put the fulcrum where a force is applied, then that force doesn't create a torque because it would have zero distance from the fulcrum. In other words, the R would be equal to 0. Now I want you to imagine taking scissors and snipping string B. What would happen?
It would fall.
The whole thing would fall straight down?
Well, like, it would kind of like flop.
It would flop. This side would fall. This side would rotate upward. What does that make string A if it's a point around which this bar will rotate?
The fulcrum.
It's the fulcrum. So if we set string A as the fulcrum, then we can find string B's tension from the torque it creates. Once we have string B, we can go back and find string A. Oops. So let's go ahead and treat this as a torque problem. String A will be our fulcrum, and then we'll go back and do the other half. String B is on this side of the fulcrum, so if it was unbalanced, then it would cause it to rotate counterclockwise. So it's the only positive torque. These two are negatives. This plus this plus this must be equal to 0 or else it wouldn't be balanced. So I'm going to move these two negative clockwise torques to the other side with the 0. That makes them positive. So string B is how far from the fulcrum? Well, the fulcrum string A, which is, according to this, distance D from the string B. So 1.2 meters. 900 newtons is at the 2.55 mark. As in from the left end, this is 2.55 meters. But 1.2 of that is on the other side of the fulcrum and therefore doesn't count. So this is its R, this lever arm right here. So just treat it as subtraction. 2.55 minus 1.2 gives us 900 newtons at 1.35 meters. Plus 25,000 newtons. And this is at 4.9, take away 1.2, 3.7 meters. Now you're going to want to go ahead and turn these two into torques by combining those. Anyone notice what I left out? There was a step I skipped. The sine theta part.
Oh.
Because this is at a 90-degree angle, this is at a 90-degree angle, this is at a 90-degree angle, this is at a 90-degree angle. And what is sine 90?
1.
1. So anything times 1 is just you get the anything back. So why bother? So I didn't bother. Tension B times 1.2 meters. 900 times 1.35 is 1215 Newton meters of torque. That's enough to open a pickle jar. 25,000 newtons times 3.7 is 92,500 Newton meters. Add those together to combine like terms, because they're both in Newton meters and they're on the same side and they have the same sign. Why not combine them? You'd be a fool not to. 93,715 Newton meters. Now divide each side by 1.2. Meters cancels out, gives us an amount of newtons appropriate for a tension. Divide by 1.2. 78,095.8. I'm going to round that to 96 newtons of tension. And remember, like I said, everything else could be done as a free body problem, which this is a good thing to do at this point of the year. It's been a long time since we've done free body diagrams, and that's a damn shame because they're so useful. So this is a nice unit to have at the end of the year because it starts to tie back in those mechanics after our interlude into electricity. So draw that free body diagram. What's the only upward force? Tension A. What are the downward forces? Tension B. The weight of the beam. The weight of the other thing on the beam. And if these come out to a sum of forces in the y-axis of 0, then we know that this is positive. These are all negative. They add up to give you nothing. So if you move those negatives to the other side, tension A is equal to all of them added together. Tension A can be found from adding them together. 78,096 newtons plus 900 newtons plus 25,000 newtons would give us tension A. Therefore, tension A is 103,996 newtons. There you go. Don't forget, these old tricks, they're still good. Just because we haven't done them since the first 9 weeks doesn't mean that they aren't still useful things. And in fact, that's why I saved this unit to last, so that this could jog your memory past some of the damage that time has done to it. Were there any other ones on this sheet that anyone wants? I guess no one wanted this one, but is there one that anyone wants? Riley, were there any that you found compelling?
There were, but like I kind of got them all through the thing you posted.
Okay. This one, what are the X and Y components? You would do that via free body diagram, balancing it out after using torque to find the tension. And then you just take the tension and split it into the X and Y, sine and cosine, and it solves really easily. So Riley, you were able to find the key and the Dropbox link, and everything worked for you, right?
I mean, it was just like some pictures uploaded.
Right, but you were able to get those pictures.
Yeah.
All right. I don't know whether everyone's being honest with me or not, but I've had a few kids say that, like, oh, I couldn't get that to work, or I couldn't read it. And, you know, everyone's internet situation is different right now. So,
Well, sometimes, and it kind of depends on what time I go on Edsby, it'll say something like, Edsby is too busy right now. Come back later. But if you just click download, and you just like save it, save the file to save the file to your computer, it works.
Okay, that works. All right, nice. I'm glad we have that in the recording so that anyone who watches this can pick up that tip. Let's do this last one because I did this one with the kids yesterday. And this will be the last of the torquey ones before we move on to the new one with moments of inertia. This one, it works better if you draw it out so that you can visualize it. We have a uniform rod Remember, uniform is important because it means that we're able to be sure where the center of mass is. Center of mass would be in the center. The center of 50 centimeters is 25 centimeters. So it has a mass of 0.2 kilos. Again, I will use 10 for gravity. 2/10 times 10 is 2 newtons. A fulcrum is placed 40 centimeters from the left end. All right, so notice that the fulcrum is not in the middle. When you are building a seesaw, the reason you put the fulcrum in the middle is so that the fulcrum is under the center of mass, and therefore you never have to worry about the mass or weight of the seesaw itself. Like if you had a seesaw with the fulcrum perfectly centered, it should just be able to sit still horizontally. Our fulcrum is not under that point, therefore the weight of this rod will create a torque. What distance from the left end should a rod of 0.6 kilos be hung in order to balance it? Well, first of all, if we're trying to balance out this torque, on what side of the fulcrum do we need another mass to be in order to counterbalance it?
The right.
Yeah, it's got to be on the right side of the fulcrum. So it should be some distance greater than 40 from the left-hand side. Of course, if we got exactly 40, then this mass would create 0 torque for having no distance from the fulcrum. But at some distance r, we have the weight of a 0.6 kilogram mass, would be 6 newtons. How far is 25 from 40? If this was a number line.
15.
Absolutely, it is 15 centimeters. And thus we have enough to do this. You could do this out as a torque problem and it'd work, and you just do torque as force times lever arm on either side. So 15 times 2 is equal to 6 times r. But that's a proportion problem. Consider it. Think of it like a proportion problem really quickly. This is 3 times as much force. And in order to balance these, we need the same torque. How do you cancel out tripling this to get this to be the same?
You got to make the R like a third of it.
Yeah, exactly. And that would cancel out and give you the third. That would give you the same rather than, yeah. So we would need to have a third the distance to go with 3 times the force. 1/3 of 15 is 5. So 5 away from 40 is 45 centimeters. Boom. It's that easy, and it's done. Or you could have, of course, done 2 newtons times 15 centimeters equals 6 newtons times r. This would end up being 30 newton centimeters equals 6 newtons r. 6 times what gives you 30? 5. So it'd be 5 away from 40. That's 45. Either one of those strategies would have gotten you the same answer. Therefore, they are equally valid. So whichever one you do, that's your preference.
Wait.
Yes.
So on this problem, like, is it the bar that weighs the 2 newtons?
Yes.
And it's at like the very center of the bar is where we're like counting it essentially.
Yes.
But wouldn't like less of it, there'd be less weight on like the left side of the fulcrum because some of it's now on the right?
Yeah. If you imagine here is 10, right? So we could think of the weight as coming from the halfway mark there. And then the 10 over here has its weight on the halfway mark here, but this cancels out that leaving us with just this. I know that's kind of weird.
What? Okay, but like, my question was like, so the total weight of the bar is like 2 kilograms, right?
Mm-hmm.
Or 0.2 kilograms, so it'd be 2 newtons.
Yes.
So wouldn't the force on the left side be slightly less than 2 newtons? Because there's some of the weight is on the right side.
You could go through and try and use, well, it's uniform, right? So you could take a certain amount over here and a certain amount over here and distribute that. But the whole point of finding the center of the mass is that you end up doing that much more simply. You could go through a different process and follow the line of reasoning that you're doing, and you would get the same thing. However, the center of mass, the whole point of being able to find that is that it will give you one place where all of the weight comes from.
Okay, so as far as like the exam is concerned, the 2 newtons is all at the center of the bar.
It's all at the center of mass, and if it's a uniform bar, then the center of mass is at the center of the bar.
Gotcha.
If you don't support the center of mass, then you effectively have a torque of the weight at however far it is from it.
Okay.
All right. Since you guys weren't that into that sheet anyway, you want to go over the new one? Did anyone have any questions off of the new sheet that is the one that looks like this? There's no key for this posted yet. And if you don't want to shout out, then I can see any responses you give me in the chat, and that won't show up on the recording for anyone who is terribly shy. But if you got requests, now's the time to make them. All right, I got something in the chat. Oh, just a notification that you got to go. Well, adios.
Goodbye, Mr. Stone.
And iPhone 2, is that Sierra again? All right, we got a request. Question number 4. A uniform stick has length L. The moment of inertia about the stick.
That's
for
5.
Oh, you caught me. Then number 4 it is. How long does a rotating object take? How long does it take? We're looking for an amount of time. To speed up from, that means an initial velocity of 15 radians per second. 2, that makes it a final velocity of 33.3 radians per second. If it has a uniform angular acceleration alpha of 3.45 radians per second squared. Uniform acceleration is another one of those key terms. And when you have uniform acceleration, you know, you can use what kind of formula?
Kinematic.
Kinematics. So we look at our kinematics and we decide which one of our kinematics is most useful for this. And I'm thinking the one that does not have displacement, because we aren't given displacement. So let's not worry about displacement. The one that doesn't have displacement in it is final velocity equals initial velocity plus acceleration time. Or another way of it is just saying the definition of acceleration. Acceleration is going to be the change in velocity over time. These two things are the same, just with some terms moved around. This one is set equal to final velocity. This one's set equal to acceleration. Other than that, they're the same. Although this one I think would be easier to move my terms around, so I'm going to plug into that one. Move the t to this side, move the acceleration to this side. And your time will be 33.3 minus 15 radians per second divided by 3.45 radians per second squared. Radians on the top, radians on the bottom. Seconds on the top, seconds on the bottom. We're going to be left with per second on the bottom. Per second means just seconds. And therefore, we get a time measurement. So we know we must have done something, right? And from here, just get out your calculator. 33.3 minus 15 divided by 3.45. 5.30 seconds. Nice, easy angular kinematics one. Would have been at home in last week's tiny quiz, I think. Which, by the way, you guys did really well on last week's tiny quiz. I was really happy to see it. Since I started talking about number 5, I'm going to go ahead and do number 5. Although, if you have any other requests, you can still post in the chat while I'm talking. But we've got a stick of length L, and it has a moment of inertia I. And the axis is the center of the stick, according to that last sentence. So we've got a stick supported in the middle, and it's going around like this. That has a moment of inertia I naught. But then we take a particle of mass m and stick it on one end of the stick. Now remember, the formula for center of mass is the sum, or excuse me, not center of mass, the sum of, for moment of inertia, it's the sum of mass times radius squared. And that depends on the shape, but for a particle that is a point mass, that is the easiest case, where you just literally use this. It's the mass and how far it is from the center. So its mass is m, and its distance from the center is r. R is 1/2 of the length. And since we're taking the sum, we need to add that to what we had before. So we have mass m at 1/2 the length. I guess m should be capitalized because that's how they wrote it in the thing. 1/2 the length gets squared. What's 1/2 squared, people? 1/4. So L squared is L squared, and then we have a fourth. So I naught plus ML squared divided by 4. Our best answer is therefore A. You probably haven't seen one of these in a while, huh? This is, of course, a fidget spinner. You probably played with this more in your middle school years than you are willing to admit now. But this is one of Boba's toys. And I dug it out of his stash of stuff under the couch in order to show it to you. If we wanted to find the moment of inertia of the fidget spinner, then if we ignore the plastic because it's so much lighter than the weights, then it would be 3, because we have 3 of them. And then it's just going to be mass times how far they are from the center. So if we call that the mass of one of these m, and then they are, I don't know, some length r away, we'd need to square that. And that would give us the moment of inertia of the fidget spinner. Because that's treating it like 3 point masses, and that is totally ignoring the plastic portion of the fidget spinner. But you'll notice 3 mr squared. If you look at some of the moments of inertia of the objects that were given on like your sheet, that's pretty freaking high. For example, for a sphere, it'd be 2/5 mr squared. 2/5. That's nothing. For a thin ring that you're going about the diameter, so like if you take a quarter and put your finger on one end and flick it so that it spins, 1/2 mr squared. Of course, that's not a thin ring. That's a disk, but still. 3 mr squared is really high. Having a high moment of inertia is going to make this thing accelerate less from an applied torque, because torque is not just force times radius, it's moment of inertia times angular acceleration. So the same torque of me flicking it, I'm going to get less acceleration from that because it has these weights on it. Why do you think they added these weights and increased the moment of inertia then? What good does that do? Why would you want something to have a high moment of inertia? It's in order to prevent it from experiencing acceleration that you don't want. For example, it might cause it to accelerate less from this torque, but there's friction in these ball bearings. Small, but it's there. And I'm going to decelerate less from that torque because it has a higher moment of inertia. So it's harder to get it going, but it's also harder to stop. Think way back to that first 9 weeks and the example of Becky and the Jeep and how she crashes into the back of 3 different vehicles, another Jeep, trailer full of Mountain Dew, and also the little old lady on the Vespa. Well, the thing that had the least inertia accelerated the least from that force. Similarly, having a high moment of inertia will make it harder for this to stop. I did get a request while I was talking, and it was, can you do either 6 or 7? Let's do number 6. A 5-kilogram sphere is connected to a 10-kilogram sphere by a rigid rod of negligible mass. So just like I ignored the plastic on the fidget spinner, we can ignore the rod's mass and not include it. Which of the 5-lettered points best represents the center of mass of the sphere-rod combo meal? Well, to find the center of mass, you could either use torque or there is an equation for it. The distance to the center of mass from one side is the sum of masses and their distances from whatever reference point divided by the sum. Why did I got this weird deformed sigma? Sum of masses. And the cool thing about this is that you can put that reference point wherever the hell you want it. So whatever is the easiest for you. For example, I like to put it all the way off to one side. There you go. So let's do the sum of mass times how far they are from that point. How far is the 10 from that point? Well, that's easy. The 10 is that point. So it has a distance of 0 from it. 5 kilos is the entire length away from it. So I'm going to call that 5 kilos times L. And the sum of masses, 10 plus 5 is 15 kilos. 10 times 0 is 0. So this doesn't matter. 5L divided by 15, because the kilograms cancel. So 5/15 as a fraction would be 1/3. L is the length of the rod. So it would be 1/3 of the length of the rod from our reference point. Which one of these points is 1/3 of the length away from our reference?
B.
B. Absolutely. And then I was asked to either do 6 or 7. I'll do you one better and do both 6 and 7. So we're looking for the greatest moment of inertia for this apparatus. Remember, moment of inertia is the distribution of mass around some point. So again, we can put that reference point wherever we want as long as we max out the moment of inertia. So if we put it at A, this is, well, it's not going to add to the moment of inertia. Moment of inertia is the sum of masses on it times how far they are from the reference point squared. Well, in that case, for case A, it's going to be 10 times 0 squared. And we all know what 0 squared is. Plus 5 times L squared. Thus, the moment of inertia around 5 would be 0 plus 5 kilogram, whatever L is squared. So that's how you'd find it for A. B is 1/3. So if we move it to B, we'd have 10 kilos times 1/3 L squared plus 5 kilos times 2/3 L, and then that's squared. 10 times 1/3 squared is 1.11. 5 times 2/3 squared is 2.22. So for B, it would be 3.33 kilogram L squared. All right, now C. It's going to be the same process, only it's going to be 10 times 1/2, because C is the halfway mark. So 10 times 1/2 L squared. 1/2 squared, as we already figured out, is 4. 10 divided by 4 is 2.5 kilogram L squared plus 5/4. 5/4, 1.25 kilogram L squared. So that's going to be 3 3/4, 3.75 kilogram L squared. And now D. 10 times 2/3 squared times, I'm just going to do this on my calculator. 10 times 2/3 squared plus 5 times 1/3 squared. It's 5. So that actually gets us back to what we had for the original one we did. E is going to be easy because this 5 won't matter and 10 will be the entire length away. So it would be 10 kilogram length squared. So which one of these had the greatest moment of inertia?
E.
E is correct. This is like in the video where I tried swinging the lightsaber from the far end of the blade from the handle, and I had like no ability to control it because its inertia was so great. It's like trying to control a runaway like Mack truck or whatever. It has so much inertia, there's not much you can do to speed it up or slow it down. Well, this is going to have so much moment of inertia, there's not going to be much you're going to be able to do to control it. And this is also, if you think about moment of inertia as like balance of mass distribution around the thing as it spins, well, this is the most unbalanced it could possibly get. You've got the most mass, the farthest it can possibly be. And I got another request for the conceptual ones, like 9, 10, or 11. I'll tell you, 9 and 10 are basically the same question. So I'll just do one of them. Were you guys able to hear that through the mic? My back cracking? We've got a disc, a hoop, and a solid sphere, all of which have equal mass. At the same time, they're released from the top of an inclined plane. This is just like in our video lecture with the 2 wheels going down the plywood ramp next to the pool out back. They're all uniform and they all roll without slipping. In what order do they reach the bottom? Well, in order to do this, you would have to know their moments of inertia. Thankfully, with this, I included a reference sheet. A sphere rolling around its center has a moment of inertia of 2/5. So sphere would be 2/5 mass radius squared. A hoop is a thin-walled cylinder around its central axis, so a hoop would be just mr squared. And finally, a disk, which would be a solid cylinder, is 1/2 mr squared. All right, for those of you who watched my video for this week, which I think is all of you, which won the race? The one with the ball bearings closer in, or the one with them further out? All right, I got the answer in the chat. Yeah, it was the one with them closer in. The one with them closer in has lower R value for the same masses, so it has a lower moment of inertia. So in order to win this downhill race, the advantage is to the object with the lowest moment of inertia. It'll be the easiest one to start spinning up, and thus it'll spin its way down the ramp soonest. So which one of these 3 objects will win the race by having the lowest moment of inertia? Sphere, hoop, or disk? Come on, you can answer in the chat if you need to, but which one of these has the lowest moment of inertia? You're right, Kirk. It is the sphere. 2/5 is smaller than 1/2, and 1/2 is smaller than 1. So the sphere wins. It reaches it first, so we can get rid of A, B, and D. Who is the runner-up that comes in second place? The disk, absolutely. And finally, the hoop comes in dead last. So our best answer is C. 10 is pretty much the exact same question. It just asks which one will win, therefore which one will win, and the sphere will win. So this is a conceptual one, but you are comparing values that are given. Again, you don't have to memorize these. Remember, ever since the apocalypse happened, everything is open notes now. So you can have this as a reference sheet. It's not going to bother anybody. You've got this. If you haven't printed it out, then maybe copy it into your notes so that you have it as a reference you can pull up quickly, either now working on like quizzes and practice sheets, or perhaps if you need it during the AP exam, well, you're going to be doing that at your home, so you can use it then. Last one I was asked was number 11. Number 11 is kind of samey. We've got 2 discs, a wheel, and a rod. So the 2 discs, according to this, the disc's radius goes up. We square that. So the bigger radius disc is going to have the greater moment of inertia. So A is not going to have the greatest moment of inertia. We can eliminate it immediately. And the nice thing about that is that just leaves us with B, C, and D, and they all have the same size. So B is a thin-walled cylinder, or a hoop, if you ignore those spokes, which I'm willing to do if you are. And according to this, it should be mr squared as its moment of inertia. C, being a solid disk, would be 1/2 mr squared. And a rod around its center axis perpendicular to the length is 1/12 ml squared, where its length is 2 radii. So we're going to have 1/12 m 2r squared. So to put this into terms that can be compared with the other guys, we're going to end up with 4/12 mr squared. That is 1/3 mr squared. So which one of these is the greatest? Wow, greatest. The B, C, or D, the wheel, the disc, or the rod. If you can answer this one, I'll be really proud of you. You're right, it is B, the wheel. The wheel is the hardest one to accelerate. Why then do you think a bicycle would have a wheel as opposed to a disc? Well, for one thing, it's going to be less material, so it's cheaper to manufacture. Also, just because it's harder to speed it up, that's not the only consideration to make. It's also going to be harder to slow it back down. So the friction against the road isn't going to like stop your bike immediately and send you flying over the handlebars. Kind of like Bo's fidget spinner. Number 12, I think, actually made it onto last week's tiny quiz. It's 100 radians per second. And number 13 is a nice, easy peasy torque problem where you have balance and equilibrium. 14, 15, and 16 are a good biophysics one. I know that everyone's going to be doctors after college, so I'm not going to deprive you of the opportunity to do in the biophysics one. You can do that one and check for it in your, I'll put the key on Edsby. But the trick to number 15, the center of mass is getting lifted to this height. So don't find the work and then assume that you put it in here. The center of mass rises this much. To do number 15, remember that the change in potential energy is equal to the work. So just find the difference from like 0 potential energy due to gravity, and then her mass gets lifted up that far, and that one becomes a lot easier. Did you guys want to do the gizmo or not? The gizmo for this week is reasonably easy. But if as much as one person wants to go over it, I'll do it. All right. Well, in that case, I'll pull it up and let's checketh it out. Torque and moment of inertia. A couple of you have tried this and asked for resets, so maybe this will make sure that your second attempt is easier. Everyone should be able to see the gizmo. And we've got two objects. We can control the mass of the bar. Of course, the bar at being massless is going to make this easier. The two objects, this one is twice as heavy as that one. So if we release it by taking these, oh God, there's a name for those things. Sawhorses? Is that what those are called? But those two sawhorses, we move those out from under. This one has the same lever arm as A, but A has half as much weight. So it should have half as much torque. So A's clockwise or counterclockwise positive torque should not be enough to balance out B's. And thus it rotates. We can show the moment of inertia. And the total moment of inertia is 3/4 of a kilogram per kilogram meter squared. If we have B way off to one side, can I drag that? Apparently not. That sucks. How do I change that? You'd think it'd let me change. Show ruler. Oh, I have to drag it down here. So if I put B all the way over here, well, then now it's got twice as much weight and 4 times the leverage. So it descends again. And if you notice, we have a lot more moment of inertia. But let's compare the time. When we have greater moment of inertia, and we can show the torque too. All right, there's our time. Let's move A over to balance it out some so that we have less moment of inertia. And there you go. We had less torque though too. If we balance them out, like this, notice that this one has twice as much weight, but we're going to give it half as much leverage, and we have balance. However, that doesn't mean it has no moment of inertia. That means the torques cancel out. You can play with it some more, but honestly, this one's nice and easy. Let's do one together. Let's do number 3. Number 3 looks easy. A boy has a mass of 66 kilos, and he's 1.2 meters from the fulcrum. A girl has 44 kilos. Where does she need to sit in order to balance out the boy? Well, she has 2/3 of his mass. So we have 2/3 the force. We need to have 3/2 the distance in order to cancel that out and get it to be the same torque. So 3/2 of 1.2 would be 1.8 meters. Easy. All right, so that's one down. You got 4 more to do. And remember, I'm giving that holiday extension. You have until Monday to get this turned into me. And you'll also have until Monday to do your end of the week tiny quiz. So lucky you guys, you've got plenty of time to get stuff done. All right, if there are no further questions, no further concerns, then I'm willing to end the meeting. Anyone got anything to share? Hopes, dreams, fears? All right. Well, in that case, adios, children. Enjoy your holidays over the weekend, and maybe get the rest of these done while you're at it. Bye, everybody. You have a good weekend too.